Change. Change view. What? What change? Transformer.
Okay, you got that? Okay, so in this lecture we're going to study transformers. Here's an example of one.
Yeah.
Optimus Prime, obviously. He's leader of the Autobots.
Yeah.
Yes. His enemy is but the person's name? Come on.
Megatron.
Megatron, yeah, okay, yeah. Decepticons, correct. No, that's not it. Not as exciting as these Transformers, I'm afraid. It's as boring as these Transformers.
Don't say drawing.
You know it's going to happen. Now, this is what a Transformer is. It's a very, very simple and very, very boring machine, but very, very useful. Let me explain how it works. So, what you have is something like a piece of copper, it's usually actually a piece of iron.
Still iron.
Iron, yeah. And then you have an alternating current which wraps around this side, the alternating current, and then comes out here. Then what you have here is a copper wire which wraps around this side and comes out. Now, this is what happens. This current here is alternating, so that means it's changing direction. Do you remember how quickly I said this changes direction? 50 times a second. Okay. Now remember, when we have a current, by using the right-hand rule, we have a magnetic field.
Yeah.
So there is a magnetic field here.
Yeah.
However, when the current changes direction, what happens to the magnetic field? Change direction as well. But remember what Faraday said. When a magnetic field changes, the delta flux, what will that cause in a nearby conductor? It will cause a current to flow in the nearby conductor. So remember, if you move a magnet, you get a current. So because this current is alternating, it changes directions. Because it changes direction, its magnetic field that's around it changes direction. And because its magnetic field changes direction, it induces a current in the second conductor. It induces a current here. So, what's the point in making a current here if we have a current here? You might say that's a waste of time. Why don't you just connect this wire to this wire and let the current flow? Well, what's very interesting is that the current you get here will have a different voltage to the current that you get here. And this is actually how you can change the voltage. In this picture here, what will happen is you'll get less voltage here. Now we can actually see the reason why if we look at Faraday's law. So I don't care about the direction for the moment. So we have voltage 1 equals N1 change in flux over change in time, and voltage 2 equals N2 change in flux over change in time. And I don't really care about the minus. Now, in these two formulas, what is the same and what is different? In fact, these will be different and these will be different. The N1 here is bigger than the N2. But what is the same as this, because there's just one magnetic field that's changing here. So if I was to divide these, I get V1 over V2 equals N1 over N2. So the ratio of the voltages is equal to the ratio of the number of turns. So if I want less voltage, I have less turns here, and if I want more voltage, I should have more turns here compared to this one. So this is a very, very simple way to change your voltage. If you have, here we go. This here is an example of a transformer. This here is 220 alternating current. However, my laptop only needs about 12 volts. So this is too high. Inside here is something like this that will take the 220 and convert it into 12. Also, inside this, it's not just a transformer. Half of it's a transformer, and half of it is to convert the AC into DC. So it actually has two jobs, this box. It's a transformer, and also it changes from AC to DC. Yeah. You know those little travel plugs that you might see in the travel plug? Yeah. You can change the voltage 110 to 220. If you break that open, you'll see something like this inside of it. Okay. And now it is time for you to draw it. This side is called the primary, and this side is called the secondary.
Secondary, primary.
Yep. Yep.
The same can be the same.
Well, same is pointless because you've just changed the voltage into the same voltage.
What happens to the 220 to 12? What happens to?
Yeah, where does the missing voltage go?
Yes.
No. What happens is, although the voltage decreases, the current increases. So in total, the power stays constant. So to answer your question, in a sense, the missing voltage has become extra charge, extra current.
So it's still stored inside the transformer?
No, it's in the secondary cable. So for example, suppose we have 13 amps at 220 and we convert that into 110. We then actually increase the current to 26 amps. In total, it balances out. If you drop the voltage, you increase the current. If you increase the voltage, you drop the current.
The primary should be bigger than secondary.
He just asked me that.
What was that? Sorry, what
Although he said it differently. He said, could the secondary be bigger?
Yeah.
The answer is the secondary and primary can be anything.
Can be anything.
Except equal, because equal is a waste of time.
I know. That means it's possible to change it from 110 to 220.
Yes. Yes.
It's possible.
Yes.
Interesting. How? How is it possible?
What do you mean, how is it possible?
That AC generator
Yeah.
send 110.
Yeah.
Then this
Makes it 220.
Is it condenser? Is there a condenser then?
Condenser?
I mean this. Okay.
Should we write the other stuff like that?
Most important thing is that you write this is primary, this is secondary, this is iron. You could even write the magnetic flux is this direction. Yeah, you can call this N1 and N2, V1 and V2.
And copper wire and...
Copper wire, iron, core. It's very important now that you understand this only works if it's alternating current, because we require the magnetic field to be changing to induce the current. Must be alternating. This is another reason they use alternating currents in the power plant, because it's easy to change the voltage of an alternating current. Cannot easily do it with DC. Yeah?
So the magnetic flux always moves.
No, it'll flip around the other direction when the current changes. Yeah. Okay, continue. So, we have our formula. A transformer is an electrical device that transfers electrical energy between two circuits through induction. The induction produces an EMF. Okay, that's a bit too much for you to write down. Yeah, that's enough. So the transformer transfers electrical energy between two circuits, and the process changes the voltage. So there's actually a little bit more to add to this definition, but I'll show you what to add. Yeah, so if you look at the picture, these are actually two separate circuits because technically they're not connected.
Two or more? Can there be three, four?
I suppose there could be, although we only ever look at two. Okay, did you write that? Now, I don't want you to write this. Instead, I just want you to jump to this, add this to your definition. So within your definition, write step-up transformer increases the voltage and a step-down transformer decreases the voltage. You can please add those to your definition. Okie dokie?
Yeah.
Yeah? Continue?
Yeah.
So, I suppose if you really wanted to save the effort, like I mean I would, but if you're being like way about it and you wanted to save yourself a few seconds, you could at least just say a transformer changes the voltage. Really I would write these 2 points in after that first sentence. Okay? Right. So I've already examined how it works. It works using Faraday's formula for induction, and we can arrive at this formula. N1 over N2 equals V1 over V2. I don't know if you have this. You can write it down. Yeah. And you might be thinking, oh, well, this is great actually, because it means we can use this to make free energy. Just increase the voltage to 1000 volts and free energy. Although it doesn't quite work like that, the power that goes in still equals the power that comes out. Yeah, that's the point. You see, because power equals IV, it means if you were to increase the V, it comes at the expense of decreasing the I. That's what I mean by power in equals power out. So, the current has an opposite relationship. If you up the voltage, you down the current, and vice versa.
What's the N?
The N is the number of loops around it. Yeah. So actually, if you put this formula together with this one, I'll actually show you, it's not that difficult to do. So P1 equals P2. So that means I1 V1 equals I2 V2. So V1 over V2 equals I2 over I1. But V1 over V2 equals N1 over N2. So it means we can end up saying N1 over N2 equals I2 over I1. So you can make a second formula here that says N1 over N2 equals I2 over I1. Got that? So usually what happens in the power plant is they make the AC, then they step up the voltage to 10,000 volts, they send it to your home. In a substation near your home, it takes the 10,000 and steps it back down to 220. It's something usually like this. I think it's 10,000. Or is it 100,000? Large voltage. Okay, let's have a look at an example. A small toy requires 6 volts. It uses 220 volts from the mains. The number of turns on the primary is 4,400. How many are on the secondary? So my first question before you calculate is, should there be more or less than 4,400 on the secondary? Are we stepping up or stepping down? Stepping down, so do we need more or less turns? Less, okay. Which formula do we use here?
N1 over N2 equals V1
Yeah, okay, so calculate the N2, please. Should be no problem, I hope.
Bam, bam. Bam, bam.
Bam, bam.
Got it.
You got it?
Yeah. Looks nice.
I hopefully made it a nice number. Ah, that's ugly.
That's nice.
That is ugly.
Oh, 1, 2.
What did you get?
Okay.
Yeah, that looks like it. I think you made a mistake. Recalculate. Let's see yours.
1, 2.
Yeah, I think this is it, yeah.
Bam, bam. One is one prime, yeah, one tan tan tan. Tan tan tan.
Is the N1 or the N2 the AC?
The AC is the N, the 1, yeah. So, it's, the N1 is 4400 and the V1 is 220.
V1 is 220.
Yes!
Yeah, V1 is 220.
Yeah, so N1 over N2 equals V1 over V2.
Oh my god.
So 4,400 over N2 equals 220 over 6. So you can solve this and you get N2, I believe, is 120.
Yeah.
Is it?
Yeah.
Yep. Continue?
Yeah.
Yep. Okay, so there you go. That was it. It's as difficult as it gets. It's a very nice exam question.
Only 2 formulas.
Only 2. It's a very, very nice exam question. This lesson. Very nice exam question. Okay, can you try these for a few minutes? Let me stop the video.